Welcome to another video from MechCloud Academy. While official documentation is a great start, the real challenge is assembling individual directives into reliable, production-ready solutions for modern applications. My name is Steve, and in this video, we'll bridge that gap by building a playbook of essential NGINX patterns. We are going to construct 6 practical patterns, moving from foundational security to advanced protocol handling. We will demonstrate not just the how, but, more importantly, the why behind each configuration, showing how NGINX can centralize security, decouple services, and handle complex requirements without modifying your application code. Let's begin. Our first goal is to protect a backend service. The modern approach is to avoid building security logic into every single application. That would be repetitive and create multiple points of failure. Instead, we'll use NGINX as a gatekeeper to delegate the authentication check to a dedicated external Auth microservice. If the Auth service gives a green light, the request proceeds. If not, NGINX blocks it. This is the foundational Auth proxy pattern. Let's trace the flow. When a request arrives, the Auth_request directive immediately fires. NGINX pauses the original request and sends a new internal subrequest to the /internal_auth_check URI. This location is marked as internal, which is a crucial security measure. It means this endpoint can only be called from within NGINX, never directly by a client. Without this, a malicious actor could bypass our protected service and call the Auth endpoint directly. Here, we proxy the check to our Auth_service. For efficiency, we also tell NGINX not to send the original request's body to the Auth service, as it typically only needs to inspect headers or cookies. The Auth_service performs its verification. If it returns a success code like 200 OK, the Auth_request is considered successful. NGINX then proceeds to the next line, proxy_pass, sending the original request to our protected user_service. However, if the Auth_service returns a 401 unauthorized or 403 forbidden, the Auth_request fails. NGINX immediately stops processing and returns that error code to the client, effectively blocking access before it ever touches our main application. Blocking unauthenticated requests is a great start, but it's not enough. For a successful authentication, the backend service often needs to know who the user is to fetch their data or perform actions on their behalf. The backend could receive the original token and revalidate it, but this creates redundancy. A better pattern is to have NGINX enrich the request with user information after a successful check. This is done with the Auth_request_set directive. It allows us to capture response headers from our Auth service and store them in NGINX variables. Let's assume our Auth service, upon a successful verification, returns custom headers like XUserID and XUserEmail. The Auth_request_set directive reads these headers from the upstream Auth service's response. We then use proxy_set_header to add these captured values as new headers to the original request before it's finally passed to the user_service. Now our backend can safely trust these headers. Why? Because they were set by our secure NGINX gateway, a trusted component of our internal infrastructure, not by the external client. This pattern decouples our backend from the specifics of authentication, allowing it to focus purely on its business logic. A real-world application is never entirely private. You'll always have public endpoints, such as a login page, a password reset handler, API documentation, or a health check. Our current gateway is too restrictive. It protects everything. We now need to create specific exceptions, or pinholes, in our security layer. The solution lies in NGINX's location matching priority. NGINX checks for an exact match, specified with an equal sign, before it considers more general prefix matches. We can leverage this by adding new, highly specific location blocks for each public endpoint we need. Inside these new blocks, we add the directive Auth_request_off. This explicitly disables the authentication subrequest for any request that exactly matches these URIs. So when a request for /auth/login arrives, NGINX finds the exact match, sees Auth_request_off, and immediately proxies the request to the login handler on our Auth_service. It never triggers the global check defined in location /. Any other request like /users/profile won't find an exact match and will fall through to the main location/block, where the authentication check is correctly enforced as intended. Now that our API access is controlled, let's address how browsers talk to it. Cross-origin resource sharing, or CORS, is a browser security mechanism. If your front-end application at ui.example.com tries to make a JavaScript API call to your API at api.example.com, the browser will block it by default. To allow it, the API server must send back specific CORS headers. While you could add these headers in your backend code, handling it in NGINX is more efficient and consistent. It keeps this infrastructure concern out of your business logic. A key part of CORS is the pre-flight request. For any request that is considered non-simple by the browser, such as one with a custom authorization header, the browser first sends an options request to see if the actual request is allowed. Our NGINX configuration must handle this gracefully. We use an if block to detect the options method. If we see one, we add the necessary access control headers, like allow origin, allow methods, and allow headers. We then return 204, which is an empty no-content success response. This satisfies the browser's pre-flight check without ever bothering our backend services. For all other requests, like GET or POST, we simply add the required access control allow origin header to the final response, telling the browser the request is safe. Let's switch gears to a different kind of communication protocol. Server-sent events, or SSE, are used to push real-time updates from a server to a client, perfect for live notifications or data dashboards. By default, NGINX buffers responses, which is efficient for normal requests but breaks SSE. Imagine a chat application. Without changing this setting, NGINX might wait until it has several messages before sending them in a batch, creating noticeable lag. We need to configure NGINX to act as a transparent tunnel for the stream. The most important directive is proxy_buffering off. This tells NGINX to forward data to the client the instant it receives it from the backend. We also disable caching with proxy_cache off, as this is a dynamic stream. Finally, we ensure a persistent connection by setting proxy_HTTP_version to 1.1 and clearing the connection header. This prevents NGINX or the backend from prematurely closing the connection. This simple configuration transforms NGINX into a high-performance pipeline for real-time data. Our final and most advanced pattern addresses a nuanced requirement. What if you don't want to block unauthenticated users, but rather show them different content? For example, a public view of a profile versus a personalized logged-in view of the same resource. In this model, the backend service, not NGINX, needs to make the final decision. This configuration is more intricate. We use the error_page directive to intercept 401 and 403 errors from the auth_request. Instead of blocking, NGINX performs an internal redirect to a named location we've called at fallback_auth. This is a powerful control flow mechanism. If the auth_request is successful, we take the first path. We use auth_request_set to capture the X-user email header from the auth service's response. If the auth_request fails, NGINX takes the second path, jumping to our @fallback_auth location. Here, we explicitly set the X-user email header to an empty string. Crucially, in both paths, the request is ultimately passed to the same user_service. The result is that the user_service always receives the request. It can then simply check if the X-user email header is present and not empty to determine if the user is logged in and who they are, allowing it to serve the appropriate content. As we've seen, by thoughtfully combining a handful of NGINX directives, we can solve complex, real-world architectural problems directly at the network edge. We've built robust security gateways, managed browser communication policies, and enabled real-time protocols, all without modifying our backend application code. Mastering these patterns allows you to build cleaner, more secure, and more scalable systems. This playbook demonstrates how NGINX can centralize security, decouple services, and handle complex protocol requirements, letting your applications focus on what they do best, delivering business value. Thank you for joining us at MechCloud Academy. We hope this practical guide helps you leverage the full power of the NGINX toolbox.